This question is about enthalpy changes. Figure 1 shows a Born-Haber cycle for the formation of strontium chloride. Table 1 shows some thermodynamic data. Use the data in Table 1 to calculate a value for the electron affinity of chlorine. So the electron affinity of chlorine is when 1 mole of gaseous atoms gains an electron to become 1 mole of gaseous 1- ions. So let's go up to our table and our Born-Haber cycle. We can see that the electron affinity is happening on this arrow here, so I'm going to label this one X, but we can also see that there's 2 chlorines, so this is going to be 2 times the value that we want. I'm going to then put on the other values that have been given to me in the table. So I can see that my negative arrows, my down arrows, I've got formation on the left and lattice formation on the right. I can also tell that my electron affinity is going to be negative because it's a down arrow. Then I have on the left, I've got the atomization of strontium happening first. So that was 164. And then I've got 2 times the atomization of chlorine, because there's 2 chlorines there being atomized. And then I've got the first ionization energy, 548, followed by the second ionization energy, 1060. So I want to calculate this arrow with the X in. So you can do this one of 2 ways. You could use Hess's law, which says if this is root A, this is our root 1, then root 2, starting at the same place but going the other way around, will have the same value. So root 2 equals root 1, so that would be 2x equals, and I'm going down this first arrow, down this second arrow, down the next arrow, down the next arrow. The next arrow is already down, but you can see that because it's all these downs, they're all negative numbers, and then I'm going up the last arrow, so that one becomes a positive number. And that could give me 2x, and I could use that to find x. Or you may have learnt the rule where this arrow here, minus 828, equals all the other arrows added together. Either of these, when you do the maths, will give the same answer. And you rearrange to find x. If you do that, what you'll find is that if I were to take, I'm just going to copy and paste it here, if I were to take my calculation that I did, and I was to complete that sum, then I would get 2x equals minus 730, and so x equals minus 365. So that's my answer, minus 365. Draw a line from each substance to the enthalpy of lattice formation of that substance. So it's not that you're supposed to know them. What you're supposed to use is your knowledge of the charge density of the ions to say which one would have the strongest attractions in the lattice and therefore the most exothermic lattice formation. So here we've got Mg2 plus and Cl minuses. Here we've got Mg2 plus and O2 minuses. So the oxide ions have a higher charge density than the chloride ions, so this would be stronger attraction, so a more negative answer than magnesium chloride. And then we've got barium and chloride ions. Now barium is a larger ion than a magnesium ion, and so it would have a smaller charge density and weaker attractions. So this is going to be first, this is going to be second, and this will be the weakest, which means that our MgO is going to our most negative number, our barium chloride is going to our least negative number, and our magnesium chloride is going to our middle value. Table 2 shows the theoretical lattice enthalpy based on the perfect ionic model, so perfectly spherical, no covalent bonding, so no covalent character. And the experimental value, that's the true value. So these two are different numbers, and they're fairly different. And what that means is that there is some covalent character in silver chloride, and that covalent character is adding strength to the lattice, and that is why it's more exothermic. Then we've got table 3 shows enthalpies of hydration values. So remembering that hydration is going from gaseous ions to aqueous ions of group 1 elements. Explain why the enthalpy of hydration becomes less. So this means weaker attractions to water as we go from Li plus to K plus. Okay, so as we go from Li plus to K plus, the size of the ion increases. So charge density decreases because it's charge divided by size. The charges are the same, sizes are getting bigger. Therefore, because the charge density decreases, there are weaker attractions between the metal ions and water. Which bit of water would attract to the positive metal ion? It would be the delta minus oxygen in water. This would be the negative part of water. Calcium bromide, CaBr2 solid, dissolves in water. Use the value to calculate the enthalpy of hydration of bromide ions. Now we've got the enthalpy of solution and the enthalpy of lattice formation. So we could create a cycle here. So the enthalpy of solution is when the solid dissolves into a solution, so it gives us the aqueous ions. And that would have a value of minus 110. Lattice formation is forming the solid ionic lattice from the gaseous ions. And that's got a value of 2176. Gaseous ions to aqueous ions are the sum of the hydrations, so it's minus 1650, and 2 lots of the hydration of bromide ions because we've got 2 bromide ions. So we could use this cycle and Hess's law to say that the route that we want, we could go the different way around. We could say minus 1650 plus 2x equals minus 2176 minus 110. So 2x equals minus 2176 minus 110 plus 1650, which is minus 636. And x equals minus 318. So we could do it that way. If you prefer, you could have learnt the equation, which is the enthalpy of solution equals the enthalpy of lattice dissociation, which is not what we've got. So you would have to change the sign on that, plus the sum of the enthalpies of hydration. So you could add up those numbers and you could use the equation that way.